Hi. So I spent the last couple of lectures talking about the physics of dipole moments and dielectric matter, but I have decided to terminate the discussion on dielectrics uh, for a number of reasons. It's a little bit too application oriented compared to the other subjects I was going to talk about, and perhaps the other reason is that the techniques that are involved to discuss the physics of dielectrics is a bit specialized to that particular theme, and not always find applications outside that issue. So instead of spending more time on that, I have decided to spend more time on things that have broader application, and also the math that I'm going to talk about has a broader implication than the other stuff that show up in the physics of dielectrics. Okay, so and before I go on, I really want to encourage you to raise questions about the lectures I already gave. And this is really helpful because, as we all agree, electrodynamics is an extremely challenging subject. So there's no shame in saying that I don't understand this or I don't understand that. It's completely natural for you to not understand some or many of the things I talk about. And to help you step up with the understanding, I think it's really necessary that we go back to some of the earlier themes and cover them um, again in a more slow manner. But I don't know what themes to go back and cover unless you ask me what are the puzzling things that you have. And that's why it's really important that you raise questions to me rather than me asking individually each one of you to tell me what exactly it is you don't understand. So yeah, please raise some questions, upload them on iCampus, or just send me an email, and I'll prepare some additional videos trying to answer your questions. Okay, so what I want to do today is to go back to this a fundamental equation of electrostatics, which gives the electrostatic potential at arbitrary position r as a function of the charge distribution function given for all the positions in space. And the relation is quite simple. It's just an integral of the charge density with the weight that falls off as the inverse distance. However, the challenging part is the actual computation is of this integral. We know that usually these integrals are impossible to perform, and therefore we're not able to get the analytical expression or even numerical expression for the potential in a reliable fashion. So we need to develop some specialized techniques to solve this problem analytically or numerically. Um, and a great development took place later, I believe in the 18th century or 19th century, where this scheme was invented to convert this integral relation into a differential relation between the potential and the charge density. So the relation says that if you take the Laplacian of the potential function, then it equals the local charge density up to some factor. And the Laplacian is nothing but the sum of second derivatives in each coordinate direction. And This differential equation seems to be quite simple, but that's only the appearance of it. The actual solution of this is usually not simple at all. So, as with any other differential equation, what this equation is telling us is that once we know exactly what the charge density is everywhere, then in principle it should be possible to find a function phi, which, if operated on with a Laplacian, would exactly reproduce that charge density. The challenge in solving this differential equation is that this is not an ordinary differential equation depending on only one variable, but rather this is a partial differential equation depending on three different variables, x, y, and z. And if anything, partial differential equations are orders of magnitude more difficult to solve than ordinary differential equations. And in many cases, it's impossible to find solutions at all in an analytical form. However, there are situations where it becomes possible to make a lot of progress in terms of the solution. And that situation is when you have no charge density, at least over a certain region in space, in which case this differential equation simplifies to the Laplacian of the potential function being equal to 0. And this may seem like an artificial situation, but in reality, this arises more often than you might imagine. For example, let's imagine the situation where we have one capacitor plate at potential V1 and another capacitor plate at potential V2, and there's nothing in between the plates, just a vacuum. And the question you want to ask is, what is the potential at some point, any point inside these pair of capacitors? And because, of course, charges only live on these capacitor plates, in the interior region, there's no charge density, so therefore the equation satisfied by the potential function is like that, and this is called the Laplace equation, because when the right-hand side of this relation is 0, then we this equation is commonly known as Laplace equation. Okay, so here's the new and fundamental philosophy in solving this problem. Although we know that the potential ultimately arises from the charge, we don't really try to solve this problem in terms of the charge. We try to solve this problem entirely in terms of the potential. Okay, so rather than worrying about how much charge is sitting, how much charge is sitting on top of this plate or on top of that plate, we just say that this plate has a fixed potential V1, and this plate over here has a fixed potential V2. In other words, this potential function, when its coordinate is equal to 0, and that's the x coordinate of this plate over here, the potential has to be V1. And when x coordinate equals L, and that's the coordinate of this second plate, then the potential better be equal to V2. And such conditions are known as boundary conditions in the theory of differential equations. And so our task is to find a function which satisfies the Laplace equation in the first place, but at the same time satisfy these additional boundary conditions when x values coincide with this special points. Okay, so now that I have laid out the philosophy in general terms, um, yes, sorry, I want to walk you through the actual process of solving this problem with an example, which is probably the simplest possible example alive, um, yet contains a sufficient amount of non-trivial procedures that will be vital in solving Laplace equations in general. And the problem is that of conducting duct. So conducting duct is this long, how should I say this? Long, it's a duct. It means it's a rectangular shape with an infinite extent in one of its directions. Okay, so it extends to an infinite distance in this way, infinite distance in the other way, and the cross section has the shape of a square and with linear dimension of L on each side. Um, and and this is consisting of metallic stuff. So each side can be put at a specific potential. And I have chosen the case where this the bottom side of the duct has potential 0, the top side has a potential v prime, and the two sides on to the left and to the right has the potential v. Okay, and now the question is to find out the potential on the inside of the duct, which at the same time would coincide with the potentials at these four boundaries. So inside, we know that this potential will satisfy the Laplace equation, but at the same time, the solution has to be consistent with these potential values at the boundary. Okay, so that's the layout of the problem, and now we're going to solve it. First of all, due to the translational symmetry, it's clear that this will only depend on two coordinates, although this is a three-dimensional system. But along the third direction, the z-coordinate, there will be no difference as you move along the z-coordinate. There's no change in the environment, which therefore will give us the conclusion that the potential function cannot possibly depend on the coordinate in that direction. And luckily, and as a result, the Laplace equation also simplifies from being a three-dimensional Laplace equation to being a two-dimensional Laplace equation like this inside the duct. And plus, there are these boundary conditions that has to be met. These are just mathematical expressions for the boundary conditions I have laid out over here in terms of a picture. Okay, so both the equation to be solved and the boundary conditions to be met seem pretty innocuous or relatively harmless, but we still don't know really how to go about solving such a problem. And hopefully you have acquired enough mathematical physics as an undergraduate student to know that the separation of variables technique comes in handy to solve this problem. And I won't go through the details of what this technique is all about, because that's really the realm of mathematical physics that should have been covered somewhere in the past in your education background. So I'm going to just go through that procedure and lay out the way we find the solution. Okay, so the separation of variables says that you can write down this full solution, which depends on both coordinates, as a product of two functions, each of which depends on only one coordinate. So this capital X function depends only on the coordinate x, and the capital Y function depends only on the coordinate y. Now, the implication of this Ansatz is a German word for guess or assumption. According to this Ansatz, this second partial derivative on x turns into a second derivative on the x function multiplied by y, because y does not contain any x dependence. And likewise, this second partial derivative in terms of y translate into x function multiplied by the second derivative of the y function. Again, because x function does not have any dependence on the y coordinate. So now this Laplace equation turns into something that looks quite a bit different. It's a sum of these two terms. And in the next phase of the solution, we're going to make an ansatz. And the ansatz is that we're going to assume that these second derivative of the x function will be proportional to the x function itself. And likewise, the second derivative of y will be proportional to the function itself. So this is an ansatz. And ansatz means that if this trick works, then fine, we will buy that. If it doesn't work, then we will just throw it out and look for some other trick. But obviously, the whole reason why I'm talking about this at all is because this trick somehow works. Okay, so let's follow up on the details of how this trick works. So according to this ansatz, this function becomes like that. So what happens is that the derivatives disappear entirely. So the result becomes just the product of x function and the y function multiplied by the sum of these coefficient proportionality factors alpha and beta. And the net result, and the product of these three things has to be zero, because that's the Laplace equation. And obviously, we cannot say that the product of the functions is zero, because that means there's nothing going on. That's a trivial solution. But what we want, rather, is a non-trivial solution. So the only option we have left is to say that this sum has to be zero, which means that this second derivative of x and the second derivatives of y are not independent, but they're rather related through this common constant alpha. Okay, so that's the equation now that we have to solve. But what are the solutions? Well, the solutions are quite easy to find, because this is nothing but a second order ordinary differential equation. One of the simplest second order differential equations. And the answer is that when alpha is zero, because we haven't really talked about what kind of values to give to alpha, we have to assume for the moment that alpha can be anything. So when alpha is zero, then the then the second derivative is 0, that means the solution has to be of this form. It's a linear function. However, when alpha is non-zero, then depending on whether alpha is positive or negative, you can have either an exponential function or a harmonic function, sines and cosines. And the nature of the solution depends on whether this alpha is positive or negative. So if alpha is positive, then the solution will have an exponential character, while the y solution will have an oscillatory character. Okay, because of this relation, if one function has an exponential character, then the other function necessarily must have an oscillatory character, and vice versa. So when alpha is negative, then x function becomes oscillatory and y function becomes exponential. But since all that is known at this moment is that alpha is some constant, we don't know whether the ultimate nature of the solution will be x exponential and y oscillatory, or x oscillatory and y exponential. That all depends on the exact nature of the problem that we have to face. Okay, but we're going to march on bravely, saying that why not take alpha positive? Again, if this ansatz fails to give us the solution, then we will just switch our position and say alpha is negative. But let's proceed on the firm belief that alpha is positive. And instead of writing alpha, I'm going to write alpha square, because by assumption that I've just made seconds ago, alpha is positive, so it's perfectly all right to say I'm going to write alpha square instead of alpha. Okay, I should first mention this. If we choose alpha equal to 0, then x is this linear function. But since alpha is 0, here, the second derivative of y is also 0. That means y is also a linear function. And since the potential is given by the product of the x and the y function, that means the general solution has to be of this form, the product of two linear functions. Okay, now let's move to the case where we assume that alpha is a non-negative, is a positive number. In that case, I can write alpha square instead of alpha. Then the equation for x will be this one, and the equation for y will be this one. And these are both familiar functions, second order differential equations, and we know perfectly well what the solutions are. The solutions for the x function is a combination of two exponential functions. The solution for y is a combination of two harmonic functions like this. Okay. Actually, that's about it regarding the solution of the Laplace equation. We have considered basically all possible situations. But what we have failed to take into account so far is the boundary condition. The boundary condition was summarized up here, or summarized as a picture over here. And now the question is, how do we make these functions, all of these exponential and harmonic functions, combine in such a way that these boundary conditions are indeed satisfied? And because there are four sides to the conducting duct, there are four sets of there are four sets of boundary conditions to be satisfied. And the trick is to start with the easiest one to deal with. We earlier saw that when y is equal to 0, that is the bottom plate of the duct, then the potential over there is 0. Now, in order for something to be 0, we quickly see that this little c over here, see, because we are going to take y equal to 0, so d times y is 0. And so the whole thing becomes c times a plus bx, but we better have this entire thing equal to 0. And the only way that can happen is if we take c, this little c is equal to 0. Okay? So that's pretty much the only option that's left to us by the boundary condition. And similarly, for this function, assuming that alpha is not equal to 0, if we take y equal to 0, then this sine part automatically vanishes. However, the cosine part does not automatically vanish. And what's left is this big constant, capital letter C, constant which better be equal to 0. Otherwise, we will not be able to satisfy the boundary condition. Okay, so already by applying only one out of the four boundary conditions, we were able to cut down on the number of possible solutions. The possible solutions are either of this form or of this form. So we roughly got rid of half of the possible solutions as being unqualified. Okay, so let's move on to the top plate where the boundary condition was that it should stay at the fixed potential V prime. Now, how about this boundary condition? How do we satisfy this? Well, actually, it turns out after some thinking that since we have this function, okay, and we're talking about y equal to L, so y becomes L. So now we have to require this entire thing on the left to equal some constant v prime. But obviously this won't happen because of this linear term. And the only way to satisfy this equation is if b becomes 0. Okay. Sorry, I should have turned off. So that requires us to set A to be equal to this potential V prime divided by L. Okay, so as a result, the alpha equal to 0 part of the solution has to be like this. Okay. But since this boundary condition that the potential be equal to V prime, this condition has already been taken care of by this linear part of the solution. The other part, namely this part, will now have to satisfy a different boundary condition. That is when y equals L at the top plate, this whole thing better be equal to 0. Because the value equal to V prime has already been taken care of by this linear function. So this function cannot add anything to v prime, which means that the value of this function has to be 0. Now, once again, this is 0 regardless of what x we choose. And of course, that will only happen if this assigned function was identically 0, which will only happen if alpha, which we assume to be some arbitrary constant up to now, take on this specialized set of values. That is, if alpha is constrained to be an integer multiple of pi over L, right, then this sign of alpha times L is always 0 because this is just sine of some multiple of pi, which is 0. So once we agree to quantize these alphas, then this boundary condition at the top plate, where y equals L, is nicely satisfied. And it doesn't matter what integer value for n you choose. Any integer will do. Now, what that means is that you actually have to take summation over all possible integers of n. Okay, so now we are able to write down a solutions to the Laplace equation in this general form as a linear combination of many possible solutions. Okay, so now you may wonder, why do I have to take a sum over all possible n's? This is like summing over an infinite series, and that's very hard. But the reason why we kind of have to take all possible cases into the sum is because unless we do that, we won't be able to satisfy the other two boundary conditions coming from the two sides. Remember, when x was either equal to 0 or equal to L, then the potential was identically equal to some constant v. Okay. Now, since this was the general form of the solution, when x is equal to 0, then this function becomes like that. When x equals L, then this function becomes like that. Sorry, out to here. And both of these sums better be equal to v. Okay, so what we have on the left hand side is a fairly complicated function of y, and another fairly complicated function of y, and yet the result after the summation over an infinite series is some constant v. Now you might be puzzled to see that this summation over many different harmonic functions, over many different frequencies, can somehow give you a constant value. But this is the sort of thing that happens all the time in Fourier analysis. And as a reminder for yourself of your old lessons in Fourier analysis, I am assigning this as a homework problem rather than going through the solution myself. So here's the homework problem. The homework is to find an explicit expressions for a_n and b_n by performing some Fourier integral. And I won't tell you the details of the procedure. The details are actually given in the book. Uh, but in any case, I want you to work through the details and find out these explicit expressions for both an and bn. And do not just copy the answers from the book. You really need to work through all the intermediate steps. So that's the homework number one. So for this week, the homework requirement is not only to make a summary of the lectures I just gave, but also to do these homework problems and present your solutions alongside with the summary, alongside the summary. And now I have a second homework problem. This entire construct was based on the assumption that alpha was a positive number. Right, let's go back and see where we have made that. Yeah, here. Here we have made an assumption, somehow arbitrarily, that alpha has to be a positive number. And it seems like we wound up successfully finding the solutions that also satisfy the boundary conditions. But what will happen if we choose alpha to be negative? Right? Then we can set alpha, instead of writing alpha, we can say minus alpha square. So this equation will become an oscillatory function, oscillatory equation, and this equation will become an exponential equation. So the roles of x and y will be switched. Now, under those conditions, can we still find a solution which satisfies both all the boundary conditions? If yes, then you should be able to work out the solution. If not, then you should be able to explain to me why this assumption of alpha less than 0 fails to produce the desired solution. In any case, your consistent answer will be required, and that will be homework number 2. Okay,